last time, I began proving a very important theorem which relates Lie homomorphism between Lie groups and differentials of this homomorphism, which are homomorphism of the corresponding Lie algebras. Ideologically, the main idea is that basically they correspond to, one correspond to each other. In reality, it is not quite so. So we need to make more precise statements. So the statement is, first, for every Lie homomorphism G, I prefer to write H into G between two Lie groups, there arises a homomorphism between their Lie algebras. This is a Lie algebra homomorphism, takes commutators into commutators. It is always reasonable to assume that H is connected. G also may be connected. At least if H is connected, then the image of this homomorphism is connected, and so lies in the component of the identity. So we can easily assume that both are connected. Now, more or less trivial part, which we did last time, is the statement that if it was part A of a big theorem, so I write A, if for two homomorphisms F and G between two Lie groups, Lie homomorphisms, and A should be connected for this, if D for this DEF equals DEG, then F is equal to G. And the proof is sort of very simple. We just consider these maps F and G, consider the set of points where they coincide, and find that this is both closed and open. It was done last time. Also, we need to have some statement that if we have some homomorphism between Lie algebras, then it corresponds to some homomorphism of Lie groups. And this is true with some reservations. So B, assume that we have some Lie algebra homomorphism. What we want to construct a Lie homomorphism F of H into G, say that the F is phi. And it is possible, again, with some reservation. What is definitely possible, and I will begin with this today, it is possible, so three different statements. There is a local homomorphism. Local, this means that actually it exists only on some neighborhood of the unity in H. And it's homomorphism in the sense that the homomorphism rule holds where it holds whenever it can hold. So if G1, G2, and G1 times G2 belong to the domain of this map, then f of G1, G2 is equal to f of G1 times f of G2. I said this last time. So this always exists. Second, actually there exists a different global homomorphism. Not of H, of some covering over H. This covering over H is also a Lie group, and this has the same Lie algebra as H. They are locally diffeomorphic, so the same tangent space at E. Say that DEF is phi. And to make this simpler, I can say, maybe it is not a very good statement, but I can say that if H is simply connected, then there exists an f of H into G with the same property. This follows from the second part because simply connected manifolds have no coverings, only the identity. So in this case, simply H tilde has to be equal to H. So the last statement does not, is actually a small part of the second statement. I want to begin with the first part and actually even with something else. Suppose that we have some subalgebra. Lemma, if you wish. Let H be a subalgebra, Lie subalgebra of G. Then there exists a local subgroup. H in G. Local means that H actually is a submanifold of some neighborhood of the identity in G. And it is a subgroup in the obvious sense. So this is the statement. Do I need to explain anything regarding the statement? Any questions? Now the proof is based on a classical fact from analysis, Fabinian theorem, which I formulated last time, and somehow we decided that maybe you do not know this. I will explain something about this, the statement and the how to prove it. I hope you will be satisfied with my explanations. So, temporarily forget about Lie groups and everything. We just have some manifold, M. And dimension manifold. Now an M-dimensional distribution. Is a family. Probably I denote them by A here. AP of subspaces of dimension M, which form a smooth family of planes. If you really prefer this language, I can say that this is a subbundle of the tangent bundle. So in every fiber of the tangent bundle, in every space TPM, I distinguish some subspace of small dimension M. M is less than N. Now, this distribution, I can denote it somehow one by one letter. Script A. This distribution A is called integrable if for every point P in M there exists a submanifold of some neighborhood of P in M. So some local submanifold says that it is tangent to the distribution. That is, for every point Q in SP, TQ SP is AQ. So we want to construct this submanifold. It's called, yes, just a second, I just want to say, it's called the integrable submanifold. Integral submanifold, integral submanifold. Yes?
I have a quick question. So the distribution is expanded by some n linearly dependent vector field, or just a distribution?
Just distribution. It is local theorem, actually. Well, no theorem so far. But the thing which I want to find is local. So you can easily assume that M is a domain in Euclidean space. Then what I say is correct, and actually the proof is based on this. But my statement will be very much local. So the classical theorem in ordinary differential equations says that if M is 1, then every distribution is integrable. So for every family of straight lines, we can find integral curves which precisely which is stated here. If M is more than 1, say 2, then actually a generic distribution which you just take by random will not be integrable. It's a very strong condition. And there is the Frobenius criterion for integrability. It says the following. Suppose that we have very much locally two vector fields, x and y. Which are subordinated to my distribution. Which means that at every point P, whenever these fields are defined, they may be defined locally in some open set. This means that for every P in the domain of these vector fields, X, P, and Y, P, the vectors of these vector fields, both belong to AP. So we choose vectors from this subbundle, from this distribution. And then I say that it is subordinated to A. Now the statement. A is integrable if and only if for every x and y subordinated to A, the commutator x, y is also subordinated to A. This is my main statement. And since you pretend that you do not know this theorem, it's a very important theorem, certainly not precisely part of my course. But since you pretend that you don't know it, I will give you some explanation why, how to prove it. Actually, you can consider it as a full proof, because I will say everything. Maybe something is needed to be checked, but check is obvious. The statement, do you understand it? If M is 1, then this condition always holds, because every vector field subordinated to, all vector fields subordinated to A, actually we can take one such vector field, which is never 0, and multiply by a function. It is obvious that the commutators to such fields also have the same form. Now, it is a good strategy to prove, when we want to prove a theorem, that something holds under such and such condition. Then it is very natural just to give it a try. We try to prove that it always holds. We construct whatever we need to construct, and then we observe that actually we need some conditions. Maybe I should say first that the only if part of the theorem is trivial. If the, well, I will need to actually some trivial things before I go to the commutators. The first trivial thing is, no, I go to the commutators. I say that if the distribution is integrable, then yes, then the commutator condition, the Frobenius condition holds. Why so? You see, if A is integrable, then we have surfaces. These surfaces SP, surfaces which are tangent to the distribution, right? A vector field subordinated to the distribution is simply a vector field which is tangent to this, to all integral surfaces, right? Now, if you have two vector fields, x and y, and within this SP, they are tangent to SP, then certainly their commutator is also tangent to SP. How to prove that? If you don't want me to say that it is obvious, it is obvious. What does it mean, actually? What is a vector field? I prefer the analytic definition of vector field. A vector field is a derivation in the ring of functions. So you can apply it to functions, and the product will hold. Now, this manifold SP is defined by a system of equations. Consider any function which is 0 on SP, and maybe not 0 outside of SP. Then, certainly, the derivative of this function with respect to a vector field tangent to SP, tangent to this level set, will be also 0 on SP. It is obvious. This is actually the definition of tangency between the vector and the surface. So these vector fields, x and y, both take functions 0 at SP into functions 0 at SP, on SP. And then the commutator also. Commutators also, because commutator is xy minus yx. So this is obvious. Now, more or less the same thing, but I want to make it clear. Suppose that again. Suppose that our distribution is integrable. And we have any vector field, given maybe on the whole manifold, but tangent to SP here on SP. Vector fields do have trajectories. I want to say the trajectory of any point within SP will be totally in SP. The same reason. Any function which is 0 on SP will be 0 on this trajectory, should be 0 on this trajectory because it has 0 derivative. Function with 0 derivative is constant if you don't know. And if it is 0 at one point, it will 0 at all points. So actually, by this way, we see that if a vector field is subordinated to an integrable distribution, then all trajectories of this vector field are contained in the integral surfaces. Why it is so important? It may be important by many reasons, but actually this implies the uniqueness. I want to say that if the only part here is done. I will not return to it. I want to say that if A is integrable, then integral surfaces are unique. Well, certainly they may be different pieces, but they match where in some neighborhood of the point. Why so? Because both contain trajectories of vector fields subordinated to the distribution. This is enough to say that, that actually these two surfaces are the same for any trajectory of any vector field subordinated to the distribution. It is contained in both this and this, which certainly means implies that they are the same. This was my sort of preliminary part for Frobenius. And now I want to spend some time explanation why the if part of this statement holds. That is, if the commutator condition holds, then the distribution is integrable. And again, my suggestion, let's forget about all conditions. We have a distribution. Let's try to construct integrable surface. And then we will not need any Frobenius criterion. I prefer to begin with the case when the dimension of the distribution is 2, because in this case I can make pictures. But actually the proof is the same for any dimension, and we will also see that. 1 is not interesting because one-dimensional distribution is also always integrable. You have a question, right? No. So we have a two-dimensional distribution. Everything in my statement is local. So I can assume what you said, that there are two vector fields, x and y, which are subordinated. This is A, subordinated to A. Everything is in some neighborhood of some point, so in one small open set. Actually, any vector field, every vector field subordinated to A is f times x plus g times y. So at every point, they form a basis in the plane of the distribution. So globally, every vector field can be at every point explained as linear combination of x and y, and then the certain coefficients of the linear combination will be different at different points. So we have two functions. Okay? Okay. Very interesting. Now this is the following. Take a point P. This is my point. Take a trajectory of x at this point. Very interesting. Now at every point of this trajectory, take a trajectory of y. We do it everywhere. What we get? Right, we get a surface. What if I say that this is the integral surface and forget about all Frobenius criteria? It is so and not so. Let us look what we are actually going to have. Maybe it will be easy to understand if I say that we do this not at one point. I take this point P. Well, I don't have this dimension on the board, but imagine that I fix in my manifold an n-2 dimensional disk, something which is transverse to this, to the plane of my distribution at this point. And I do it at every point of my disk. So actually I have a family. I can have n-2 parameter family of such things, which are good candidates for integral surfaces. Please ask questions at every moment. Then the following. Why is a good candidate? I'm definitely sure that if A is integrable, these are integral surfaces. Right? Because if A is integrable, then all these curves which now are on the blackboard are contained in an integral surface, being integral curves, trajectories of vector fields x and y subordinated to the distribution. And this is two-dimensional, so all we have. And now I just want to understand whether this is an integral surface. For this purpose, I need to ask her frank answer to the following question. What is an integral surface? You know, if we define vector fields as derivations in the ring of functions, then the most, how to say, most reliable, most convincing explanation about integral surface is the following. If we have a function which is constant on every integral surface, then it should have zero derivative with respect to any vector field subordinated to this distribution, right? This is precisely what we need. So suppose that we have some function f in the neighborhood of my point P, which is somewhere on the picture. What I want to prove that, so the function is defined in some, I want to prove that xf is 0 and yf is 0. And as soon as I prove this, I won. Because this means precisely that if it is true for any function, again, which is constant on my projected surfaces, my suggested surfaces, on every surface, then this should be true. And if it is true, then my surfaces are actually integral surfaces of my distribution and B1. Okay? Because now, let me, first I want to say that of these two conditions, at least one holds. Which one? At least one holds immediately. My surfaces, you know, contain all integrals, all trajectories of the field y. Look at the picture. All right? So all the absolutely all trajectories of the field y within my neighborhood are contained in my surfaces, right? So yf is 0 because on every trajectory the function is constant. So trajectories of y are contained in the surfaces. What about x? Well. For x is not so clear. But still, there is one trajectory of x which is contained in my surface. Only one, but still not 0. Right? So xf is 0 on this thing. On the trajectory of x for which I first took, right? And this is all. Look. Take xf and take yxf. Then it is xyf plus the commutator of x and y f, right? What is this commutator? It is fx plus gy, because it, according to our condition, belongs to linear combination of x and y. Yf is 0. Very interesting. So for the function xf, we have this actually 4-term equation, but 2 terms disappear. xf, when I apply y to it, is equal to f times xf. What do you think about this equality? I personally have a very strong opinion that this is a linear differential equation for the function xf. We can actually, if you prefer to have a function of one variable, you can consider this function only on the trajectory of y. Anyhow, this is a differential equation for the function xf. I say linear, it is linear. Actually, it is possible to find an explicit solution for it, but I don't need it. But I need to say that first order differential equation has a unique solution, and 0 is a solution of this, right? Unique solution. Xf and 0. I mean unique solution if I have, excuse me, I need to say this. If I have some initial condition, the initial condition is that xf is 0 on this trajectory. Yes. So if we, for example, consider this function xf only on the trajectory of y, it's a function of one variable, which is 0 at one point. And then this condition makes the solution unique. The uniqueness theorem, nobody has cancelled it. And hence, the two solutions both satisfy our conditions. xf and 0, they should be the same. xf is equal to 0, which completes the proof of Frobenius criterion, at least for dimension 2. I'm not sure that you will be very much impressed if I say that for any dimension this will hold. Simply, if we have three vector fields, x, y, and what, and z, right? Then after we construct this two-dimensional surface, make it three-dimensional. For every point of the surface, take a trajectory of z. And then you need to apply this simple construction twice. First, you will prove that, so you need to prove that something is 0. First, x, well, I will not. Let me say that the transition to higher dimension is the same. We made the transition from dimension 1 to dimension 2. Then we will not have any serious difficulties in doing this for high dimensions. Well, questions about Frobenius criterion? You believe? Sounds convincing. And actually, this is a very important theorem. So you always, those of you who are here today, always have something from this lecture. Because this is a very important theorem, very much beyond the Lie theory. This is a theory from analysis. We will have another Frobenius theorems here, other Frobenius theorems here. Frobenius was a mathematician very broad, but this is one of his famous results. Now, I turn to proving my theorems. So first of all, I have this lemma. It was formulated somehow. It is not here anymore, so I repeat it. We have a Lie subalgebra H in the Lie algebra of G. And then I do the following. I actually explained this last time, if you remember. So this is the identity E in G. This is H, a plane in the tangent space to E. Then I apply to it all left translations. And I get a distribution on G, globally given distribution on G. The commutator condition, the Frobenius criterion, holds because, so distribution is integrable. Why? It is integral because there are left invariant vector fields. So we choose some basis, E1, EM basis in H. We consider left invariant vector fields on G. This simply the space generated by these left invariant vector fields is close to the vector of the commutators because actually this is the same as Lie algebra H. If you take linear combination of these fields with functional coefficients, again you will see immediately that the commutators of such vector fields also are such vector fields. So this is an integrable distribution. And we have, for example, for E, integral surface. And the very last point in the proof. The distribution, is left invariant. Is invariant with respect to left translations, right? Then integral surfaces also must be left invariant because they are unique. If you take an integral surface and apply left translation, what you get another integral surface. If you take this small piece actually and take any element, say h in this, then you can apply lambda h to this, and you get a new integral surface, and they will be matched at h. Both contain h, they will be matched at h, which means precisely, absolutely precisely, that this is a subgroup. Need more explanation? So this is a local subgroup, and it's done. It was not precisely what I wanted, what I need. But let me now do what I need. What I am able to do in the remaining 10 minutes. Suppose that we have a homomorphism, phi of the h into the g. Very interesting. Homomorphism is not a monomorphism. It can have kernel, and I don't want to deal with kernels. So what I want to do is the following. There is a thing which is called, well, maybe I will use short notation G and H and G. And this very much linear map has a graph in H times G. What's a graph? You know what it is. You consider the set of all pairs H, phi of H. Such a linear subspace. I say linear subspace, but it's not just a linear subspace. H times G is a Lie algebra. It is very obvious. The product of Lie algebra is again a Lie algebra, very obvious structure. And this is a subalgebra, If phi is a homomorphism between Lie algebras. And this is an immediate computation of immediate checking. So we have a Lie subalgebra in G, H cross G, right? So in H cross G, this is H, this is G, or maybe better say this is A, this is G. This is a point in the product of Lie algebras. And we have this, well, I don't need to repeat it again. We have this Lie subalgebra, and according to the previous part, there is a Lie subgroup. You can denote it as you wish. A Lie subgroup which with this Lie algebra. It has projection onto H and G. But the projection onto H, is an isomorphism, local isomorphism. Because the same is true for Lie algebras, right? This Lie algebra, when you project it onto H, just you cross out the second coordinate, it will be H. So if you combine, the projection of this graph is a copy of H. You project it onto H, it will be an isomorphism, right? So the same is true for Lie groups, because we have the theorem that the homomorphism between Lie algebras determines the homomorphism between Lie groups. So this projection is an isomorphism. And we have actually a map locally given, everything locally, a locally given map of H into G. And this part of my theorem has been proven. You have a question? Please.
Yeah, I'm confused the last part.
So, this is a product of H and G, and it has projections onto H and G both. K is a local subgroup of G cross H, right? Its projection onto H is an isomorphism, everything is local, local isomorphism, because the Lie algebra map the differential is an isomorphism. The proven part of my theorem says that if two maps have the same differential, two Lie homomorphisms have the same differential, they coincide. So this is a local isomorphism. And this is something. And I want to say that, so we get a map of H into G, locally given. And the corresponding Lie algebra homomorphism is given by this graph. So it is our homomorphism phi. Believe?
Yeah, I believe.
You have to. Now I have 6 more minutes, and I want to globalize this. And for this, I will do something incredible. So first you will laugh at me, but then I will laugh. You see, this picture certainly is not complete. This picture is complete because we actually have not just, again, in G cross H cross G, if you prefer, we have a distribution, right? And these integral surfaces are everywhere, and actually they are, everything is left invariant, so it is clear what they are. Now I define a new topology in H cross G. New topology. So for every point P here, I have a uniquely defined, locally uniquely defined integral surface, and I declare open any open set here in this surface. What can I say about, so a very new topology in H cross G, very strange. What can I say about this H cross G with this new topology? I can say that it looks now, actually H cross G is M plus N dimensional manifold, if M and N are dimensions of H and G. But this more looks as an M dimensional manifold. All right? Is it any possible? Is it any possible to introduce a structure of an M-dimensional manifold on a domain in an M plus N-dimensional space? Certainly something should be not quite okay here, and I can say what is not quite okay. Manifolds, when they are defined with some crazy conditions. And one of them is countability. A manifold should have a countable atlas. I personally do not think that you can find a countable atlas in this crazy M-dimensional manifold, which we have just defined, because this we have in this, if you wish, we have an uncountable family of these pairized disjoint charts. No. This is not possible in a manifold. What to do with this? We have strange difficulty, and it can be resolved by just one word. Can you guess what word? In this crazy manifold, we take a part which is what? Path component of identity. So, we have this M-dimensional atlas, and then we take the point EE, and we take paths within our manifold. So paths actually are tangent to our distribution, right? And this point can be joined with some other point, maybe not with all points. So I take the path component of EE, and I denote it as H tilde, and you will explain to me why I choose this notation. It is because it is a covering of H. The projection of, we have a projection of H cross G onto H. Every chart in H, in our strange topology, is projected diffeomorphically, right? So this H cross G with this crazy topology looks like a covering, with one small reservation. Coverings are connected. It is a part of definition of a covering. Without it, the theory doesn't exist. So, yes, we take this path component, and it will be H tilde. And I claim, at this moment when I have 5 more seconds, that it is the end of my proof. This H tilde is a Lie group, because it's a covering over Lie group, H. This H tilde has the same Lie algebra as H, because it's always true for Lie groups and their coverings. And then this H cross G has also projection into G. Into H is a covering, into G it is something. But my manifold H tilde now, my Lie group, is mapped into G. With all this left invariance condition, it will be obviously a homomorphism, and the differential Lie algebra corresponding Lie algebra homomorphism is our given homomorphism, which ends the proof in this strange way. We do not apply any construction, we just pronounce words. It is always easier. Just say, take a path component. Path components exist always for every topological space. And in this case, it will be a manifold, obviously. And it will be covering over, even without it. Manifold not. It is covering over H. Covering over a manifold is always a manifold. Covering over Lie group is always a Lie group. So we don't need to say anything else. My theorem has been fully proved. Next time, well, my time is over, just one word. Next time, I want to answer the question which also should be answered negatively if we don't do anything. Still, we globalize the second statement about homomorphism. Can the first statement be globalized? A Lie subalgebra of a Lie group gives rise to a local Lie subgroup. What about global? And these very easy examples, simple examples, show that it is not always a Lie subgroup, what we get, but some simple argumentation shows that the example which you know with the binding of torus is basically the only example of this. Nothing else. Thank you for your kind attention.